Hello everybody, I am Sudhan Sharma and today we will be talking about block 2, that is your numerical computing 2. The unit 1 we will be talking about will be interpolation. Interpolation is a quite important topic, not only from the computer's point of view, it is very much applicable in every field. So far as your mechanics is concerned or electronics is concerned or any other concerned field is there. You could apply it into the academics also, statistics also, and that's so. So how could it be applicable? Actually, interpolation is a term which is widely used when you want to find out the data for which you had not conducted the experiment. Say you had conducted an experiment and for some values you find you had got some observation. In order to understand, say you are having a thermometer, say, and you are observing a temperature, and the temperature shown by the thermometer is different, whereas the actual temperature is different, and you are going to plot a graph in between the observed temperature and the actual temperature. Say at some temperature x1 you are finding some the actual temperature is y1, and some temperature x2 you are finding the actual temperature is y2. Now you had finished the experiment, but you want to know if some value x arises in between x1 and x2, what will be the actual temperature at that value x. Now this is the problem. So one option is rather you repeat the experiment again and have the value at temperature x, and other thing is you use the mathematical tool which is interpolation, which we are going to discuss right now, and using that interpolation you can find the temperature at that very temperature x. So it is not restricted only to temperature, because I took the example of temperature because a thermometer is in the reach of every second person, and everybody understands the same. You can apply the same concept into the computers also. So let's have a look at what is the definition of interpolation. That in order that while you are talking about interpolation, you are finding the points in between the points. That means when n points or n plus 1 points are there, n plus 1 nodal points are there, you are trying to find the points in between those 2 points or those successive points. That means you are indirectly finding a polynomial which is to be which is best approximated, which is best fitted in those points. So you are indirectly finding an interpolating polynomial which is best fitted into these points, into these nodal points. Now the technique of finding the polynomial is quite important, and you may simply find the interpolating value by using this equation of line or by using the Taylor series, but most prominently used and promising methods are Newton forward difference method and your Lagrange interpolation method. So what I want to say that the definition of interpolation is the calculation of function value when in between the values which are already known. So the problem of interpolation can be briefly stated that, say, a function fx is defined by table of its value for a certain finite set of x. That is, for every value of x you are having some function fx, and where I is the value varying from 0 to n at the interval of 1. Now to compute the value of function fx, say you find the value xi, and which is not in the table. Now how could you find this value xi, which is lying in between two values x0 or any of the xn? Then to find this value of xi, you are supposed to use the concept of interpolation. This is the example which I had cited just now. Say that thermometer is there and its least count is 2.5. At 5 degrees C, the correction is plus 0.8. That means the actual temperature is 5.8. And at 10 degrees C, say the correction is minus 0.4. That is, the actual temperature is 9.6. Now, if the temperature occurs, if the thermometer shows you 7.5, then how will you find the value? One of the graphical approach to find the value is shown over here. That over here, by simply using the equation of line y minus y1 upon x minus x1 is equal to y2 minus y1 upon x2 minus x1, where y is the temperature which we are supposed to find. That means the correction, that is, y is the value which is question mark shown on y-axis, and 7 degree is the, or 7.5 degree is the temperature which is shown on the device. So by simply using this formula, you could find that the correction at 7 degree is plus 0.32. That means the actual temperature is 7.32. So this is quite simple, but there are some limitations. We did not to go into those details. So actually, while finding the points in between the points, we are indirectly finding the interpolating polynomial. So if fx is the function at the node x are the nodal points fx are the function values at those nodal points, and in between the discrete data of x and fx, you are finding the interpolation points, and the polynomial fitted in between these nodal points and these interpolated points is known as interpolated polynomial. Now the conditions of interpolation are that the interpolating polynomial should be equal to the function itself, and the derivative, the first derivative of the interpolating polynomial should be equal to the function's derivative. Now the error, we had already talked about error. The error is the difference in between the actual value and the interpolated value, and this error could be found out by the difference in between the fx and the interpolating polynomial px, which is shown over here. Now if a single point is given to you, that means only a single point, say the experiment is just started and only one reading you had taken. Before that no x and no fx was there, then in that very situation how you could find a value just before the first reading? In order to find that value, we are using the concept of Taylor series, and Taylor series is all you know that it is f naught plus x minus x naught f naught dash plus x minus x naught to the power n upon n factorial and f n x naught. So that the derivative increases as the value of the series increases. Now again, whenever you are finding the results, as I had already, the example I already cited, that if you are supposed to find the value 3 into 1 by 3. Now the answer will be 1, and many will say that 3 into 1 by 3, since 0.333 up to infinity, it will be 0.99999. So the actual value and the found value is the 1 minus 0.999. So the say up to 10 places you are finding the value. So point and 9 times 10 times of 9. So the difference will be 0.9 times 0 and then 1. So this will be the error. So obviously over here, as and when we truncate this Taylor series, some error will be incorporated, and this error makes the result to differ from the actual results, and this difference will be fx minus pnx, which turns out to be x minus x naught to the power n plus 1 over n plus 1 and factorial into f naught n plus 1 for this xi. Now maximum error also can be found, because in some cases, say we are finding the value of sin x or cos x. Now at 0, when the value is 0, cos x is maximum, and when the value is pi by 2, sin x is maximum. So accordingly, in order to find the value to be maximized, we are supposed to find the respective values of the interval. Now in the n plus 1 point interpolation, two methods are widely used, and they are discussed in your syllabus. They are very much in the syllabus. First is Newton divided difference interpolation method, and second is this is Lagrange interpolation method. Now in this again I would like to say that n plus 1 points are there. That means x1. You need to understand this methodology, that x1 up to xn are the nodal points. That means these are the, say, the values on the instrument, and fx1, fx2 up to fxn are the actual values, or the function values which are obtained by applying those nodal values x1 to xn. So xi, fi is the discrete data, and you are supposed to find the values in between these discrete set of data. So we are using the concept of interpolation, and the polynomial fits in between this data is the interpolating polynomial, which is Pnx. So there is an important comparison in between the two methods, that is their Lagrange interpolation and Newton's divided difference interpolation. There is an important property which is known as permanence property. The permanence property says that by adding some factor into the previous value, you should be capable to find the next value. That means Pn could be obtained by adding some factor into Pn minus 1. This permanence property is very much existing in the Newton's divided difference technique, whereas in Lagrange interpolation technique, this permanence property is not present. So Newton's divided difference methodology is quite accurate and is quite efficient. So let's discuss about this Newton divided difference interpolation technique. As the terminology is already discussed, that x are the nodal points and fx are the values of the function at those nodal points. So we are not going to discuss it again. Now let p and x be the interpolating polynomial, and for different nodal points, the expression which can be obtained will be a naught is plus a1x plus a2x square up to an xn. Now, when x is equal to x naught, that is first nodal point, then what will be the interpolating polynomial value at the first nodal point will be, by substituting x is equal to x naught in the expression of p and x, we will get the function p and x naught. And because x naught is the nodal point, so at that very nodal point, this interpolating polynomial will be the function itself, so it will be f naught. So that's why it is written that f naught is equal to p and x naught. Over here you can see that f naught is equal to p and x naught. Similarly, at the next nodal point, we can have x1 is equal to p and x1 is equal to f1, and we are having the respective interpolating polynomial. So similarly, we can have n plus 1 equation. Now, from these n plus 1 equation, we can derive a determinant which is known as van der Monde determinant. Now, you may see that this is the set of equations, and we are deriving a van der Monde determinant. For a naught, there is no x parameter, so x to the power 0 is there, so all are to be 1. And over here we are supposed to have p and x naught, p and x1, and over here we are supposed to have x naught, x1 and also. So the van der Monde determinant is shown over here, p fx. This is for px interpolating polynomial, which is for x naught is f naught. For x, x is the nodal points, x square is the square of the nodal points, and xn is the nth power of the nodal points. Now, when n is equal to 1, we are going to have the linear interpolation, and for n is equal to 1, we can have at the most x1, that is first nodal point, and the function at the first nodal point. So the determinant, the van der Monde determinant, will reduce from n cross n to 3 cross 3, and we will be having this. So by solving this determinant, we will be having the data in the format of this. We will be having this equation. Now, after rearranging this equation is very important. P1x, x1 minus x naught is minus f1, because it is the rearrangement of this equation only which provides the Newton divided difference method as well as the Lagrange interpolation method. So after rearranging, you find that the interpolating polynomial for n is equal to 1 will be fx naught plus some term is added into this, and that is nothing but your permanence property. Into the past nodal point, you are adding some factor and you are getting the interpolating polynomial at the next nodal point. It is x naught, we are having the value at p1. So this difference, this fx1 minus fx naught, could be written as f1 minus f naught upon x1 minus x naught, and this ratio, this f1 minus f naught upon x1 minus x naught, is nothing but your first divided difference, first order divided difference, and it is mentioned over here like this. So similarly, when n is equal to 2, we will be having three things. Now this van der Monde determinant will now become 4 cross 4. So we will be having the data fx naught, fx1, fx naught, x1 and x2, because 3 nodal points will be there. 2. So 0, 1 and 2. So 3 nodal points, 0, 1 and 2. And similarly, we will be having this ratio, that is the second order divided difference will turn out to be x1, fx1, x2 and fx naught, x1. Now you mind it that it is a second, when n is equal to 2, the first factor should not involve 0 and second factor should not involve 2, and the difference will be of the entire range, that is 2 minus 0. So that's why it is f1, f2, this is the initial, 0 is omitted, and over here 2 is omitted, and difference is between 2 and 0, and over here it is also between 2 and 0. And we had these fx1, x2 and fx naught, x1 are nothing but first order divided difference, and they could be written in the same way as they are written in the previous slide. So we will obtain this expression which could be rearranged into this format. Now this you need not to cram this method, because it is very much understandable that first variable is x naught, so function should be f naught, and since x naught is the term to be considered, so next two terms x1 and x2 are to be subtracted. Second is x1, f1, so first term should be x1 and the rest two are x0 and x2, so they are to be subtracted. And similarly for f2, so first term should be x2 and rest two terms are to be subtracted. So in the same way, we are using this factor, by using this data, by using the permanence property again, we observe that the interpolating polynomial will be nothing but fx0 plus first order divided difference into x minus x0 plus second order divided difference into x minus x naught into x minus x1, because n is equal to 2, so x minus x2 is not present over here. So similarly for n nodal points we can have the data. One important note to be considered is fx naught x1 is equal to fx1 x naught, and similarly the other data. So let's apply the concept which we had understood just now in the form of a numerical. Say some random data is given to you. Here we are giving you I, so n is equal to 2, I is equal to 0, 1 and 2. A discrete data is given to you in this tabular format, and we are supposed to find the interpolating polynomial by the Newton divided difference method. Now x is the value, nodal points are 0, 1 and 3, and the value of the function at the nodal points are 1, 3 and 55. So you can simply say that I 0 to 2, so n is equal to 2, and similarly x varies from 0, x0 is 0, x1 is 1 and x2 is 3. And you can also point out that f0 is equal to 1, f1 is equal to 3 and f2 is equal to 5. Now just apply the interpolating polynomial formula for n is equal to 2, which is nothing but fx naught plus fx naught x1 x minus x naught plus fx naught x1 x2 x minus x naught x minus x1, and the data available is this. So by applying this data on this formula we can have this. Same can be done by, because it might be a problem that how you will find fx naught fx1 or how you will find fx naught x1 and x2. So you can use the concept of divided difference table, that the data this minus this is forward difference we are applying, f1 minus f0 upon x1 minus x0, which is 2. Similarly f2 minus f1, that is 55 minus 3 upon 3 minus 1, that will be 26. Now the second choice is x0, x1 and x2. So second order divided difference will be this minus this upon minus. Now the difference in between x is 3 and 0. So 26 minus 2 upon 3 minus 0 will be nothing but 8. So by substituting the respective value into this equation, you will find that 1 plus 2, 2 is over here, 1 plus 2, x minus x naught is 0, yes x naught is 0, plus 8, yes 8 we had found out, and x minus x naught x minus 0, and x minus x1 is 1. So you will find that the interpolating polynomial is 8x square minus 6x and plus 1. We will do the same numerical by the Lagrange interpolation method, and we will compare that the interpolating polynomial produced by two methods is identical, although the permanence property is preserved in Newton forward difference method, but it is not preserved in the Lagrange interpolation method. But before going into the details of Lagrange interpolation, we are supposed to consider some of the details about the forward difference and the backward difference, because they are the backbones of the divided difference method offered by Newton. So let's discuss the same. So in the forward difference, please show the slide. Now two methods are available. This is a forward difference method, and the symbol is for delta, and the backward difference method is inverted delta. Now the difference is that in one method you are having fn minus fn minus 1, and in other you are having fn minus 1 minus fn. So although the results produced by the two methods are same, but they are having their advantages in their respective type of problems, because in some situation you don't know the successive value, and in some situation you don't know the preceding value. So under the non-availability, because the task of interpolation is to find the data which is not available. So in order to find the data which is not available, which may be successive or which may be preceded data, so we are supposed to use that very technique, which is forward interpolation, forward difference, or the backward difference. So let's see what the difference is. Please show the slide. That in forward difference we are having, say, delta yi. So delta yi is the function, so delta fi, you can also say that delta yi will be delta yi plus 1 minus yi, because we are taking the successive value yi plus 1, so the difference in between the two will be yi plus 1 minus yi. So second order divided difference del square yi will be delta of delta yi, and delta yi is already known to you, that it is yi plus 1 minus yi. So by opening the brackets, you can find that is delta yi plus 1 minus delta yi. Now what will be delta yi? It will be successive value of yi plus 1 minus preceding value. So it will be yi plus 2 minus yi plus 1, and delta yi will be yi plus 1 minus yi. So by opening the same, by solving this and rearranging, we will get yi plus 2 minus 2yi plus 1 plus yi. So in this situation, in this manner, we can find the kth forward difference, and we can say that it turns out to be delta k minus 1 yi plus 1 minus delta k minus 1 yi, and where I varies from 0 to n minus k at the interval of 1. Two important notifications are that the rth order divided difference are constant. If rth order divided, say you are taking first order divided difference, second order divided difference, and at the rth interval you find that they are constant, then all the differences of that order higher than r are 0. Then all successive, because they are constant, and constant you will find that more or less they will be of the same magnitude, and since they are of same magnitude, so 2 minus 2 in the successive divided difference will be 0. So it is to be noted that rth order divided difference are 0 are constant, then successive divided difference will be 0. Second important observation is that delta r, that is the rth order divided difference of the interpolating polynomial is equal to 0, then the polynomial is of degree n. You can monitor this also from my previous slide when I did the numerical, that this is constant. The second order divided difference is constant, it is 8, and it is second order. So the order of the polynomial should be 2. Yes, order is 2. It is 8x squared. It is quadratic. So the highest degree, highest thing available is 2. So the second order divided difference will find the polynomial, that what should be the maximum power of x. So these are two important observations. So the kth order divided difference is now available to you, that you can say that delta k yi is equal to delta k minus 1 yi plus 1 minus delta k minus 1 yi. So that means for every, this relation should hold good for every value of I. So let's check the same, that for y1 it will be y0 plus delta y0, and so it will be 1 plus delta y0. Similarly, you can say that y2 will be y1 plus delta y1, and by using the above equation and by modifying it, rearranging it, you will find that it is 1 plus delta square y0. So next good relation which you are going to find is yk, that means at the kth forward difference will be 1 plus delta to the power k y0. That means if you know the initial value, then by simply applying this formula to the, you can have the value of the kth forward difference. And this is also mentioned over here, that 1 plus delta to the power k is an operator on y0 with the exponent on the delta indicating the order of the difference. So k is the order of difference. So so the difference, this difference operator, what we are doing is actually we are differentiating. Yes, you may understand the same, that when we are interpolating some data in between the two, we are finding the niche in between the two. So we are differentiating the interval, and that the differentiation is done by the difference operator. And this may be, the difference operator may be forward difference or backward difference. So by induction, we can say that yk is equal to 1 plus delta to the power k y0. And if all those things are, because it is already communicated that this has got permanence property. So this in the expanded form we could have that yk is equal to y0 plus k delta y0, and then in the successive term we will be having k into k minus 1 upon 2 factorial del square y0, and so on. That means k into k minus 1 up to k minus n upon n factorial del n y0 will be the expanded form for this variable yk. So how to find del y0, because this is the issue, how to find del y0, del square y0. So it is also discussed that you can use the divided difference table. How you can use the divided difference table? X is given to you, y is given to you. So y1 minus y0 will give you del y0. y2 minus y1 will give you del y1. Mind it, y0, the indices is preceding. All the difference is from the successive value. y1 minus y0 is del y0, y2 minus y1 is del y1, and so yn minus 1 will be del yn minus 1. So again repeating the same process, del yn minus 1 minus del y naught will be del square y naught. Del y2 minus del y1 will be del square y1. And this may be repeated again. So by using these findings of del y naught, y1, y2 up to yn, del square and del cube, we can use them in this expression and get the data of yk, get the value of yk. So the same is true with the backward difference. In this backward difference, we are using that we are subtracting the preceding value from the successive, that is del yi will be yi minus 1. So by del square will be del yi minus del yi minus 1. So similarly you can have that del k yi will be del k minus 1 yi minus del k minus 1 yi minus 1. Now the order is opposite, and we are reducing the value of I by minus 1 in every cycle. So del yn will be nothing but del yn minus 1. Del square yn will be del yn minus del yn minus 1. So by using this concept, this previous equation, that del yn is equal to yn minus 1, you can solve this expression for del square yn, and you can get the data that yn minus 2 yn minus 1 plus yn minus 2 is nothing but del square yn. So in the same fashion, you can have the data of yn minus k will be del 1 minus del to the power k yn. So again we can have the polynomial yk by using the backward difference, and where we can find the backward difference values del yn, del square yn and del cube yn by using the backward difference interpolation table, backward difference table, which is shown in this next slide, where we are subtracting. Now over here the value in the, say, x naught up to xn values are given, y naught up to yn values are given. So x are nodal points, y are the functions at these nodal points, and del, that is the first divided difference, will be the successive value, that is yn minus 1 will be del yn. So nth term, n minus 1 is del yn. Yn minus 1 minus yn minus 2 is del yn minus 1. Similarly, yn minus 2 minus yn minus 3 is del yn minus 2, and you can proceed it to find the values of del values, del square values, del cube values, and use them in this equation to find the value of yn minus k. So let's apply this and use to find some values. Say forward difference table is to be found for the value that the nodal points are given to you 1 to 5. The values at these nodal points are also given to you, and you are supposed to find the value of del. So del, this is the difference operator. So what will be this? This minus this. So 2.808 minus 2.105 will be nothing but 0.703, and similarly by difference, by subtracting, you can find the difference table, and in last you will find that it is turning to be constant, that is minus 0.002. So the Newton forward divided difference interpolation formula would use forward and backward both, and we had seen that it is preserving the persistence property, and by using the formula can be expressed that yk is equal to y naught plus k del y naught plus k into k minus 1 upon 2 factorial del square y naught plus so and so k into k minus 1 k m minus n plus 1 upon n factorial del to the power n y naught. So we can use this is what is done in my previous example, where we had found the interpolating polynomial. What we had found is was nothing but your yk. So out of that discrete data, which is xi yi, which is given to you. So the Newton forward difference interpolation formula can also be modified to the Newton-Gregory forward polynomial, where x is a new variable which is introduced, and it is equivalent to nothing but x minus x naught upon h, where h is the step size. H is the step size, which in the first could be 1, and which in the successive could be 2, and so on. So it is an undimensioned variable which represents distance of x from x naught. So that is the unit of h, that is the heights. The Newton forward difference formula, by using this parameter, that is by replacing x minus x naught by h by x, we can transform this Newton forward difference formula y naught plus x del y naught plus x into x minus 1 upon 2 factorial. When you solve this factor, this value, you will find that it is turning out to be capital X into x minus 1 upon 2 factorial, and to del square y naught, and so on. And this new formula is nothing but Newton-Gregory forward polynomial. So let's use the data again, that we can use this polynomial to find the derivatives, because the ultimate motto is to find the derivatives. Then by differentiating 1 time, 2 time, 3 time and 4 time, we can have the different sequences for that is by this is the Newton, this is nothing but your Newton's formula, Newton's forward difference formula, and by differentiating this we are getting this. Now what is the use, what is the fun of differentiating them? This is well understandable by taking an example. So the example is given to you. Say some data 1, 2, 3, 4 up to 8 are the nodal points, and y values are given at these nodal points. So what you are supposed to find the value at y 2.2. Now you can monitor that 2 is given, 3 is given, 2.2 is not given. So what should be the value of this function at y 2.2? So so by using the forward differencing, that is the linear, quadratic and cubic interpolation, that is by taking linear means n is equal to 1, quadratic means n is equal to 2 and cubic means n is equal to 3, we can find the values of 2.2. How we find the same? This is the Newton's formula which is given to you, Newton's forward difference divided difference formula. Now the n is equal to 1, that means linear interpolation, that is 2 nearest points are given to you. So n is equal to 1, that means first point is x naught is equal to 1, y naught is equal to 2.105 from the table. Next point is x1 is equal to 2, and and the value at that point is 2.808. So step size is 1. So x minus x naught by h, so h is always 1, and the forward difference, you can find the forward difference which we had found that this is 0.703. So delta f naught is 0.703 and x minus x naught, x is the value which is to be found, y 2.2 is to be found. So 2.2 minus 1, 2.2 minus 1 is 1.2 plus y naught is the value given, that is 2.105, and you will find that by linear interpolation you are finding that the value of is 2.9486. Is it lying in between the value of, yes, 2.2, the value at nodal point 2 is 2.808, 3 is 3.614 and 2 point is 2.94 something, 2.9486. Yes, it is lying in between these two. So this is obtained by using linear interpolation. Now by using the quadratic interpolation, we are supposed to use n is equal to 2. That means x naught, y naught, x1, y1, x2, y2. And again using the values in your either Newton-Gregory or Newton divided difference interpolation formula, you will find that the value turns out to be 2.961. And similarly for n is equal to 3, you can take 3 values, that is x0, y0, x1, y1, x2, y2 and x3, y3. So as it is already discussed that you are interpolating something, you are finding a polynomial, whereas exact polynomial is also there. So the difference in between the find value, the value find by your calculation, that interpolated polynomial, and the value which is actual, they may deviate to some extent, and that extent is nothing but the error. So the error in Newton's divided difference interpolating polynomial and the actual polynomial will be maximum, and that error, this maximum error could be found by using the formula which is shown on the slide. This is shown over here. Please show the slide. This maximum will be maximum product. This pi, we are using the product for the difference in between the nodal points, and the maximum of this value, this nth differentiation of function at the nodal point and n plus 1 factorial, where this xi is a value which is lying between the 0th nodal point to the nth nodal point. You are supposed to understand pi 0 to n x minus xi, that 0 to n pi x minus xi is nothing but the product of values x minus x naught into x minus x1 into x minus up to x minus xn. So how we can use this? We could consider this use of error determination in our examples, which we will see in our successive slides. But before that, we are supposed to emphasize the error in linear interpolation and quadratic and cubic interpolation, because they are quite efficiently used and they are easy to calculate in the exams also. So error in the in linear interpolation, that means n is equal to 1. So two nodal points are given to you, x0 and x1, that is n is equal to 1. So pi will be 0 to 1 and x minus xi. So two multiplications will be there, x minus x0, x minus x1. And secondly, 0 to 1, that means n is n plus 1. You see the formula, it is n plus 1. So n is equal to 1, so that will be double derivative and upon 2 factorial. So you will find that maximum of this. So you can, whatever function is given to you, it may be sin x or cos x or whatever function is given to you. So you could find the value and say the double derivative will be x minus x naught into x naught minus x1. So you can in turn find that the maximum error will be x1 minus x naught square 2 and upon 8. So and into maximum of the double derivative of this function. So same could be applied to the parabolic interpolation, that is when quadratic, that is n is equal to 2. On the same pattern you can find that the maximum error will be h cube, because n plus 1, so it could be, it is third derivative, h cube by 9 square root 3, maximum of 3 derivatives of this function. And hence for n plus 1 point, similarly you can find that n minus x naught, and this error formula will hold for the nth interpolation points. So in order to understand that how the formulas of error can be used, let's consider an example. That what is the interpolating polynomial for the function? This function is given to you x square plus sine pi x through 0, 0, 1, 1 and 2, 4. So x and nodal values and the value of function at the nodal value is given to you. That is 0, 1, 2. So x is 0, 1, 2, y are 0, 1, 4 and 0, 1, 4, and you could find the difference in between the forward difference. 1 minus 0 is 1, 4 minus 1 is 3 and 3 minus 1 is 2. So by using the interpolating polynomial formula, you could find that it is, because the interpolating polynomial formula is yx is equal to y naught, that is the first nodal point, plus x into forward difference of y naught upon 1 factorial, x into x minus 1 del square y naught upon 2 factorial, and by substituting the successive values, y naught first value is 0, so 0 plus x, so x value is there, and del y naught is 1, so 1 upon 1 factorial will be 1, so it is 1 plus x. Similarly x into x minus 1, 2 upon 2 factorial, and will turn out to be x square, and degree is this and 2, so again you can monitor that degree is 2, the second order is there, and the polynomial is x square. So the exact value is to be computed, so f half is computed and turns out to be half square plus sine pi by 2, and since sine pi by 2 is 1, so it will be 5 by 4. But whereas the interpolating polynomial which you had calculated is nothing but it's turning out to be x square. So by using this value we can have f half to be 1 by 4. So this is the value which is produced by your interpolating polynomial, and this is the exact value which should be produced by the function. So there is an error, and this error is nothing but f half minus y half, which is turning out to be 1. And the maximum error in the quadratic interpolation, as you know, is given by the formula h cube by 9 square root 3, maximum triple derivative. So we are supposed to find the triple derivative. The triple derivative of the function which is given to you, and this is nothing but x square plus sine pi x. So by differentiating it 3 times, you will find that it is minus pi cube cos pi x or minus p cube cos px. And by using the value in the formula for this quadratic value, you will find a 1 by 9 root 3 maximum minus pi cube cos pi xi, because xi is the interpolating value which is lying in between 0 and 2. So when cos will be maximum, the cos is maximum when xi is 0. So we should consider the value of xi as 0, and it will turn out to be 1, and the maximum error will be p cube by 9 square root 3. So again we are supposed to consider the concept of the Lagrange interpolation. So Lagrange interpolation is also quite interesting. We are again considering the van der Waals determinant, and by using this van der Waals determinant we are deriving the linear interpolation by using 3 cross 3 determinant. And again, as I had already conveyed, that the rearrangement of the determinant solution available is quite important, because it is only this rearrangement which is contributing to 2 different methods. So when you rearrange this, you will find that it is turning out to be x1 minus x naught x1 minus x naught, x1 minus x upon x1 minus x naught into f naught minus x naught minus x upon x1 minus x naught. So this is, first is Lagrange interpolation, first coefficient L0, and second is Lagrange coefficient L1. And you suppose to remember that when naught is there, the operation performed is x minus x1. So and in denominator it is x naught minus x1. When L1 is there, it is x1 minus x naught. So first term is related to this coefficient. So by using these values you can find this Lagrange interpolation polynomial. Lagrange interpolation polynomial, and it is quite interesting, and you will find that the results obtained by the Lagrange interpolation polynomial and the results obtained by Newton interpolation polynomial are quite similar, and you can apply the concept understood by this under this Newton's divided difference method to the Lagrange interpolation method, and you will find that they are matching altogether. Altogether, the Newton divided difference method is having the persistence property, so it is somewhat better than Lagrange interpolation method. We can discuss Lagrange interpolation method in our successive presentations, and more or less you will be able to do the same by applying the concept learned in this session. And by this I would like to sum up. Thank you.